actually do it, that this depends on the number of not yet falsified rules that are in your hypothesis space that are consistent with your query, X. And this entropy, right here, is minimized when the number of hypotheses that the rule that would be ruled out is equal to the number of hypotheses that wouldn't be ruled out. So you can basically, no matter what the answer is, because you don't know what the answer will be. So when they're exactly half. Like I said, there's math. I know this is math, so maybe I should spend a little more time on that, but trust me. And we can actually understand it better graphically, where basically optimal information gain occurs where your query is true for exactly half of the hypotheses in the space. And in this example, you have 256 rules. You actually gain a full bit of information when it rules out 128 rules, and you gain less information than when it doesn't. And everyone understands this intuition because when you do 20 questions, you always ask male or female because that way you can rule out half of them immediately. So that seems like a problem. But then, of course, there's an additional consideration, which is that it seems like people actually can't enumerate all the hypotheses in the world. In fact, most people are in a situation where you have to figure out the correct hypothesis out of an entire space, but at any one point, you can't enumerate them all. You can only have a few in working memory because of processing limitations or whatnot. So the question is, what's the best strategy in this case? And so to answer that, we'll go back to the previous work and note that what they all did is they relied upon an assumption of sparsity. I don't think any of them actually called it sparsity, but it's this insight that rules that are sparse are those that basically capture a minority of entities. So pets is a sparse rule because most things in the world are not pets. Divisible by 10 is a sparse rule because most numbers aren't divisible by 10, and so on. And non-sparse rules, actually, it's kind of hard to come up with non-sparse rules, but composite would be a non-sparse rule. Most numbers, in fact, are composite, that is, they aren't primes, and so forth. But the sparsity assumption just says, well, most of the hypotheses in my space will tend to be sparse. So if you have that assumption, if in fact that assumption is true, then what happens is that false will be the most common response to a random query, right? Because most rules will return no for any random thing that you say. And the nice thing is that false is very informative if you have a positive test strategy, and actually not very informative if you have a negative test strategy. And that's where the advantage comes in. The positive test strategy makes the typical case very informative, whereas the negative test strategy makes the atypical case informative. And this is why it's actually a good thing. So intuitively speaking, then, essentially, having a positive test strategy helps overcome the bias in the world for giving a no response. So this, again, is your sort of great, wonderful, if you can enumerate all the hypotheses sort of situation, what would be optimal? If you can't, and you ask a random query, again, you sort of don't know what all the hypotheses are, if you ask a random query, it will on average eliminate about however many, or S is the sparsity, it will on average eliminate the sparsity number of hypotheses. Whereas if you ask a positive test with a positive test strategy, you can maybe eliminate slightly more because you're kind of, making it more likely to eliminate at least some rules, that is, those rules you're currently considering. In simulations, we can actually run this through and find the same results, so that if you look at the number of queries required to, and how that affects your cumulative probability of success in sort of a small world, the negative test strategy actually isn't very good. It doesn't eliminate many of the unseen rules, and that's because most of them tend to be sparse. Whereas a positive test strategy is nicely eliminating rules you haven't even thought of, which is really nice and convenient, as well as the ones that you are currently considering, which is frustrating but also convenient. So the interim summary then is I've shown that positive test strategy is actually more effective at identifying the correct rule out of an entire space of hypotheses, assuming you can only consider a few at once. If you can't, then ultimately the best rule strategy is bisection, and also that hypotheses in general tend to be sparse. And it's because basically you're overcoming a bias in the world towards saying no. But here's the question: why think that hypotheses are sparse? Well, that's been, doing all the work for us, and so it would be nice to be able to think that. And there's two reasons, one empirical, one theoretical, that I'll quickly sketch through. An empirical reason, at least in the domain of number rules, comes because we actually ask participants to list their hypotheses, which, maybe they don't have full conscious access to all of them, but it gives us nevertheless a sense. And what you find is that their typical number rules tend to be sparse. So here I've listed all the hypotheses thought of by at least two participants on the y-axis, and right here I've listed is the sparsity of that particular rule. And what you can see is a few of those rules aren't very sparse, so even in odd numbers, everyone listed those as hypotheses. They aren't sparse because each of them picks up exactly half of the numbers in the world. All of them is not sparse. Some of them are hard to interpret. Some people like important dates as like a key hypothesis, and that's probably good, but I have no idea what their important dates are. It's probably sparse unless someone really likes every date, but you don't really know. But the point is, most of the rules that people came up with are actually quite sparse. Prime numbers, divisible by 5. We had some nerds in our sample. Fibonacci came up. And moreover, it's not just that we find this in the number game, just introspection seems to give us some reason to think that sparsity is reasonable in other domains. Like I sort of was motivating earlier. But why should this be? And what I'll argue in the next 4 minutes or something is that sparse hypothesis spaces are a natural consequence of preferring hypotheses that are coherent. So when you think about it, why would you want a hypothesis in the first place? And what it seems like is that we're systematically biased towards proposing some hypotheses over others, and it's not necessarily because of sparsity, so even numbers seem a bit better than Fibonacci numbers. What it actually seems to be is probably some kind of bias towards internal coherence of some sort. Even numbers seem to have some stuff in common with each other to an extent that Fibonacci numbers don't quite so much, but that's still better than random collections of numbers. So what we'll propose is simply that people will only consider rules in the first place that reach some sort of threshold level of coherence. And if you have that presumption, then you can basically calculate the probability of including a rule in one's hypothesis space given its sparsity, the number of rules at each level of sparsity, and then from that the expected sparsity of that space that people are evaluating over. And here's what you find. I'll explain the intuition behind this after showing the graph, but basically if you look at how sparsity changes as the coherence threshold changes, you find that low thresholds imply that the space is fairly unbiased. You have rules that are sparse and non-sparse, and it kind of washes out, and that makes sense because you're including all the possible rules in the space. But as you set the threshold higher and higher, then you get more and more sparse rules in general, as a space. Although you might still have a few that aren't. So the reason we see this, we can actually illustrate by starting with some raw similarity data, in this case over digits, but it doesn't really matter. And look at the rules corresponding to every possible subset of entities, so the power set of all possible entities in the space. Again, this doesn't really depend on it having a certain similarity structure. And what we can do is we can plot the rules and their sparsity and coherence and how that changes. These are 1,000 randomly chosen rules, and these are the rules. And what you see is this interesting shape. And the shape is non-arbitrary. In fact, it directly follows from the central limit theorem. And the idea is that non-sparse rules basically aggregate over the similarities of lots of different things, so it just generally tends to come out around 0.5 sparsity, whereas really sparse rules can be very coherent or very incoherent. So here's some examples. On one end, these are non-sparse rules. Everything that is not a cat or a dog, or most of the digits except for a few, all of those have similar coherence because it's including almost everything. Whereas you can compare it to a rule like chalk and cheese, which is actually really fairly incoherent, or a rule like cat and dog, which is fairly coherent. So the sparse ones tend to vary a lot more in coherence. Now, if we set a threshold then for considering a rule as a possible hypothesis, then that will change the average sparsity of the space. If we set the bar low, then most rules are deemed acceptable, and the sparsity is about 0.5. But as we get more discriminating, then something interesting happens. So So watch this bar as it changes. So far, not much is going on. But as we go up, the sparsity, that's the red bar, goes down very rapidly. It basically emerges when you require that a rule be coherent. So, and that's exactly what causes the pattern that you see here. And at a deep level, this is an aside, but if any of you saw Dan Navarro's talk this morning, this actually occurs for the exact same reason as the size principle for generalization. So, in sum then, what I've tried to show is that basically first an extension of what other people have shown, which is that positive test strategy is actually a good idea, not just when you're evaluating one rule, but when you're looking at trying to pick out the best rule over an entire space, assuming you can't enumerate all the rules and do the optimal bisection strategy. And moreover, that sensible rule selection produces a space that is biased towards sparsity, and that's exactly the case in which the positive test strategy is useful. So, that's it. Yes, Rob.
Yeah, from the experimental data that you had, that when you asked